Okay, so the big thing about growth and decay is exactly what it sounds like. Growth means it gets bigger, decay means it gets smaller. Now the thing about it though is these are considered exponential functions, and I'm gonna brief, even though we're gonna talk about graphing tomorrow, I'm gonna briefly go off to the sideboard and just kind of explain what happens in an exponential function. So an exponential function, when you go to the far left, it's very, very flat. And as you go to the right, as x increases, the graph starts to increase big time. Almost to a point to where if you go far enough to the right, it almost looks like it's going straight up. But we know that graphs can't go straight up because those are not functions. They're not allowed to, that would fail the vertical line test if it went straight up. So imagine this, like if I gave you numbers, let's say this point right here is at 1. And then this point right here, it's at 2. But then this point right here, it's at 4. And then this point right here, it's at 8. And then this point right here, it's at 16. You notice how the numbers are changing? They're doubling. So basically, this is the graph to 2 to the x power. So every time I increase the exponent by 1, that means I'm going across the x-axis only by 1, by a little bit. It starts to grow more and more the further you get away from 0. And that's exactly true about a decay model. A decay model does the same exact thing except in the other direction. On the left side, it starts high, and as you go to the right, then it just kind of flattens out. So you're going to have to know these graphs for tomorrow, but I'm going to do an official lesson tomorrow on that stuff. Every single one of these has a real-life application. A lot of times in real life, they talk. You guys know what radiation is? Radiation is like a contaminant, and it's bad for you. And so when something gets contaminated with radiation, it has what's called a half-life, and it's an exponential model. And so bank accounts, you guys know about interest and all that stuff? That's also, it could be exponential. So you're going to see a lot of those types of questions today. Population growth, sometimes those can be modeled by exponential equations. We have a formula here that you're going to have to know. It's really easy to remember. It's actually 2 formulas in 1. So on the left side of the formula, it just shows you the final amount. So it's basically like your answer after you plug everything in. This A is the initial amount. So like let's say we're going to do a banking problem, and it says you put $500 into an account. That would be the initial amount. That's your A. Now the parentheses part, that's the most important part, because that part right there, that's your growth factor. Now it's weird because when we talk about growth means it could be getting bigger or it could be getting smaller. And that's weird for people because you think usually when you hear grow, it means bigger, right? Things can grow smaller also. And that's why we have this plus or minus here. When it's a plus, that means it's the growing kind that gets bigger. If it's a minus, that's the growing kind where it's shrinking. Then up here you have this exponent, and that exponent right there is what makes this a growth model. Anytime you have these exponential functions, you're going to have an x up in the exponent spot. In ours, it's going to be the amount of time that passes. One thing that I want to remind you, I want to make sure you understand how to read some of these questions. Sometimes they'll say the year 2000 represents t equals 0. So the year 2000 means t equals 0. So then they'll say, find the amount in the year 2007. Now here's the problem that I get all the time when kids get this wrong. What they do is they put 2007 up here into t. Are we supposed to plug in 2007 though? What does it mean when I plug in 2007? You guys understand what that's saying? What does it mean? No, that's not what it's saying. You're gonna measure, like let's say it's population. You're gonna measure the population not 7 years later like we were intending. You're gonna do it 2007 years later. So you got to be careful with how you plug this stuff in. Don't plug in 2007. Plug in t equals 7, and Can you guys all figure out how I got that? T equals 0 is 2000, right? 2001 would be T equals 1. 2002 is T equals 2, and so on. So that's the first thing that I want to correct, because it happens all the time. If you plug in an exponent that's in the thousands, your calculator is going to freak out. It's going to go into scientific notation because it can't handle numbers that big. Because, I mean, think about what happens to the graph. Look at how fast this went. It only went to 4. It went all the way up to 16 already. So imagine putting in thousands. That's going to be a ginormous number. So we don't want to do that. Okay, so what you're going to have to do is you're going to have to figure out whether or not it's growth or decay. You got to tell me the growth factor. Now, guys, you might want to circle this. When I ask you about the growth factor, I'm asking you about the number that's inside of the parentheses. Both parts. And you're going to be asked that in the questions that we're going to do here in a minute. We probably won't do every single question because I think you'll get the hang of it after a couple. But what we're going to start off by doing is we're going to try to figure out, looking at a model, if it's growth or decay. Now remember, if it's a plus, that's growth, and if it's a minus, it's decay. And don't forget also, R, a lot of times in math, R represents the rate, and rates are usually in percents. So when we do our calculations, we're going to have to turn a percent into a regular number. So you can't put percents in. Okay, so turn the page. Check this out. I got tons of questions here. There's no math to do. All I want to know is, can you tell if it's growth or decay? Now, I'm going to give you a hint. You can tell if it's growth or decay by looking at the numbers in the parentheses. So let's consider, I don't know, number 41 right here. Do you guys think this is growth or decay?
Decay.
Okay, I'm going to put the letter D right here for decay. How about in 42? Okay, you think that's growth? How about in 43? So you think that's decay. 44? Growth. 45? Growth. 46? Does anyone see a pattern here on how to tell if it's growth or decay? What's the pattern? Exactly. Anything above 1 is growth, and anything below 1 is decay. And the reason why, I messed up, I went to the wrong page. No, it's at the bottom. The reason why is because of the formula. If you already have 1 in the formula and you add anything to it, it's going to go over 1. So that's automatically growth. If you start with 1 and you subtract something from it, it's going to go under 1. So that's automatically decay. Now there's some weird ones though. Take a look at number 47. What's 47? Is that growth or decay? Why do you think it's growth? What does that mean, 5 over 4? Why does that make it growth? Yeah, 4 over 4 is already 1, so if you go above it, it's going to be higher than 1. So this one is actually a growth. What would 48 be? Yeah, and if you're not sure with fractions, you can always divide them in the calculator and hit the FD button. Is it FD? Yeah, FD. So that one's going to be decay. Okay, I want to go through a couple of them and talk about the initial amount. What's the initial amount in number 41? The initial amount, let's go back to the formula and see where we find initial amount. So your initial amount is the number that's in front of the parentheses. So let's go back over here. So what's our initial amount in 41? 4. So that means A equals 4. Oh, these are all easy. Well, you know what? Let's talk about 48 then. What's the initial amount in 48? Yeah, so the initial amount is always found in front of the parentheses, right? If it's blank, it's a 1. So that means our initial amount is just 1. And guys, I'm going to tell you something. Like, the reason why that works like that is because your initial amount is when your time equals 0, right? So think about this. What do you get when you have an exponent of 0? Type it in your calculator. Type any number and type it to the 0 power. It would give you 1, right? So really, in 43, this would be 30 times 1. That's why the initial amount is always found in the front, because the initial is at 0. And no matter what that number is in the parentheses, it just turns it into a 1 every single time. So that's why you find the initial amount in your front. Let's see, what else did they ask? Oh, the rate. What's the rate? Don't we usually find the rate inside of the parentheses? Okay, so let me ask you this. In number 41, is the rate 0.8? Okay, we got to be careful. Let's look at the wording over here in this formula, down at the bottom. R is the rate. 1 plus R is called the growth factor. So when you look at the result, that's called the growth factor. I just want the R though. So how could we find the R if this formula right here was supposed to say 1 plus R?
Oh, you subtract.
Yeah, you just subtract it, right? Yeah, so this one means R equals 0.2. What would the R be in number 42? Because this is like 1 plus something, right? Oh, actually, you know what? On this one, I messed up. That's supposed to be 1 minus R, because it has to be smaller than 1. This would have to be 1 plus R. So what would R have to be? 2? Yeah, it's just 0.1. So R equals 0.1. So let's see. I showed you how to tell if it's growth or decay. I showed you how to find the initial amount. It's always in front. And then the rate. You can. And guys, if you don't know how people are coming up with this answer, take 1 minus R and set it equal to 0.8. Solve for R. That's how you can do it to every single question. And you should know if it's plus or minus, because plus means higher than 1, minus means lower than 1. It's pretty easy so far, right? Okay, the rest of it is just application. Application means use the formula and plug it in. So our formula, let me talk about the formula. Let's see. The formula was something, A of t, I think, equals A, little a, and then 1 plus or minus R, yeah, put a t up here. So we don't usually plug stuff in here, not yet at least. The things we're going to plug in are the A, the R, and the T. So those are usually the 3 main ones that we're going to plug in. So A is the initial amount. What's the A in problem 13? Okay. So this is A. Now it says 65%. That's your R. Yeah, that's the other thing you got to be careful with. When we put that into our problem, it's actually 0.65. To turn a decimal into, to turn a percent into a regular decimal, you take wherever the decimal's at, and you just move the decimal left 2 places. So that's why it's 0.65. Sales increase. So they want us to create a model. Now, you notice how I left this blank? Should I use plus or minus? Yeah, keyword, increase. If it's an increase, it's going to be plus. So I'm going to show you the difference between a model and actually solving it. So watch this. On number 13, we're going to create a model. Here's what the model would say. A of t equals 10,000. 1 plus 0.65 to the t. So guys, a model has a letter in the exponent. So you just don't plug in that other number. And we couldn't because it doesn't even give us another number anyways. Now, if I wanted to get an actual answer, I would say, tell me the amount of sales after 4 years. But you don't have that information. So that's why at this point, we can only create a model. And I'm telling you this because that's on the test. It says, create a model. I have kids that put a number here. As soon as you put a number, it's not a model anymore. It's the answer. So we got to know the difference between creating a model and getting an answer. Let's see what we got. Blah, blah, blah. It's all the same. Let's see what this one says. Let's do 17. This looks like an actual problem. It says the population of a city has been increasing by 2% annually. The sign shown is from the year 2000. So I already see 2%. What is 2%? That's the R, right? And that's the key word right there. Increase means when we use our formula, we're going to use plus. And we're not going to plug in 2. Let's see. All right, put 2 right here. So 2 is like point like that. We got to move it 1, 2 like this. So it's actually 0.02 when we plug it in. Write an exponential growth function that represents the population T years after 2000. So it's not saying 2,000 years later. It's saying that many years after the year 2000. Now, it's not asking for an answer. It's just asking for a model. Do we know the initial amount, though? Yeah. What is it? Yeah, it's in the sign. The population of this city is 315,000. So if we're going to create a model for part A, looks like this is a population model. We're going to have 315,000, parentheses, 1 plus 0.02, and because it's a model, we just leave a T. Now part B wants us to use our model. It says, what will the population be in 2020? So the question now is, what do we need to plug in? Yeah, this right here, this actually means T equals 20. So using our formula from part A, now we can plug in the last number. And that all goes in the calculator now. 315,000, 1 plus 0.02 to the 20th power. So do me a favor and type that in. Now guys, because we're working with decimals and raising them to exponents, it's going to give you decimals, and that's okay. So after you type it in, you end up with 468,073.4. Let's see, nearest 1,000. That's 10, 100,000. So I gotta go 3. 297 means that it would be 430. I'll put a comma right here because I can't read that without it. So that means in the year 2000, there was 315,000 people in this town. At that growth rate of 2%, by the year 2020, there's going to be 468,073 people, and maybe a couple of babies. I don't know what 0.4 is. So that's growth and decay. That's what it's all about. What do you guys think? Difficult? Not too bad, right? Not too bad. You know the difference between plus and minus, plus growth, minus decay, initial amount. So I don't think it's that bad. So that's where I'm going to stop so you can start practicing.